All right, we're going to begin chapter 3 now, and we're going to continue to talk about differentiation. We have introduced that in the last chapter, and what's going to happen here in the next couple of sections is we're going to discover some differentiation rules, and we're ultimately going to pull away from limits. Okay, now all of our differentiation formulas are based on limits, but we're gonna learn what would be shortcuts now for calculating a derivative. So in section 3.1, we're going to look at derivatives of polynomials and exponential functions. The first theorem says that the derivative of a constant is always 0. Okay, let's look at a proof of that. Suppose that we let f of x be a constant. The derivative of a constant, or f prime of x, would be the limit as h approaches 0 of the difference quotient. Okay, so I'm using the limit definition here, and f of x plus h would be c, there is no x's, right, minus f of x, that's c, all over h. C minus c is 0. Limit of constant is always the constant, right, so you get 0. All right, the derivative of a constant is always 0. Another theorem, okay, if n is some positive integer, then the derivative of x to the n power is where you bring the power in front and then reduce the power by 1. We sometimes call this the power rule. Okay, we'll be using the power rule all over the place for the entire course. Here's a proof of that. So I want to have you guys kind of see where a formula is coming from based on a couple of calculations. X squared minus a squared is the difference of two squares. It'd be x minus a times x plus a. X cubed minus a cubed would factor as x minus a times x squared plus ax plus a squared. X to the fourth minus a to the fourth. You could also look at that as the difference of two squares, right? It'd be x squared squared minus a squared squared. And so when you factor the difference of two squares, of course, make sure that the signs are different. X squared minus a squared times x squared plus a squared. X squared minus a squared is going to factor further as x minus a times x plus a. When you distribute x into these two terms and then distribute a into these two terms, you have x cubed plus a times x squared plus a squared x plus a cubed, okay, etc. Now, something that I want you to notice here is that in this trend, we are always starting off with x minus a. Okay, so if I want to factor x to the n minus a to the n, I'm going to start off with x minus a, just like I did over here with these other calculations. Now, the expression after is going to be where you're adding up a bunch of terms here, and it looks like whatever the highest power of x is, you're going to reduce that by 1, okay, for the leading term there. All right, so if I have x to the n, that first term is going to be an x to the n minus 1. And the powers of x are going to decrease by 1 as you go term by term, and then the powers of a are going to increase by 1 as you go term by term. By the way, the last term, the power of a is going to be the same power of x, which again is 1 less than the power that was originally given to you there, whatever that n value is. Okay, so a to the n minus 1 would be the last term there. Okay, and so this would be just kind of a general formula for factoring x to the n minus a to the n. Now, let's let f of x be equal to x to the n. Okay, we want to find the derivative of x to the n. Well, for this proof, I'm going to use the alternate version of the derivative formula. Okay. The limit as x approaches a of f of x minus f of a over x minus a. F of x is x to the n, f of a is a to the n, and now the reason that I'd want to use the alternate version here is because when I factor the numerator x to the n minus a to the n, I have this x minus a leading off, which can cancel with the 1 down under, right? Of course, I can't make a direct substitution because I can't divide by 0. So let me go ahead and cancel those x minus a's. And I'm going to have what you see here inside the parentheses resulting inside this limit. Now, limit of a sum is the sum of the limits. Constants can come out of limits, right? So I can distribute the limit notation into each and every one of these terms and then plug in my a value. So I'm going to have a to the n minus 1 plus a times a to the n minus 2 plus a squared times a to the n minus 3 right down the list. Now, the next thing you're going to do is you're going to keep the base and add the powers on all these other terms. A times a to the n minus 2, that would be a to the n minus 1. A squared times a to the n minus 2, that would be a to the n minus 1. Okay, you're going to get a to the n minus 1 on every single one of these terms. Now, how many terms do you have that you're adding that are all the same? Well, there's going to be n of them. So check it out here. If I have, here's 4 terms that I'm adding, n was 4. Here's 3 terms that I'm adding, n was 3. Here's 2 terms, n was 2, right? So I'm adding n terms together. And, rather than adding the same number n times, I would just simply take that number and multiply by n. I get the same number when I do that. Okay, but that's what I had to get to, right? This concludes the proof that if you find the derivative of x to the n, you're going to get n times x to the n minus 1. All right, now the general power rule says that if n is any real number, you can bring down the power and then reduce the power of x by 1. Okay, this proof here was just simply for when n was an integer, but the rule applies to any power of x. You can do that. All right, so having seen that, let's take a look at some examples. Okay, suppose that I have f of x equal x to the 6th, and I want to find the derivative. Well, I can use the power rule. Bring the power of 6 down, reduce the power by 1, and so you get 6 times x to the 5th. The end. Way easier than using limits. Now, if I were to use the limit definition on something like this, that would be very brutal and time-consuming. Okay, that would be a half-page minimum of work. Okay, and so that's kind of what I was talking about earlier here, is that we're going to be using the shortcuts now, and we're going to kind of pull away from limits. I mean, all the differentiation rules are based on limits. Okay, so it is important that we prove these things as we go along, so that we know that what we are doing here is true. Here's another example. G of x equals x to the 100th. Okay. Well, I would hate to use the limit definition on something like that. Okay, but I can go right to the answer by using the general power rule, right? Bring the power down, reduce the power by 1. 100 times x to the 99th is the answer. Okay, how about what if we had y equal 1 over x cubed? Now, something that we're going to learn in the next section is called the quotient rule. Okay, we haven't talked about that yet. This is a quotient, okay, and we'll talk about the quotient rule. But the idea in this problem would be to rewrite it so that I can apply the power rule. 1 over x cubed, that's the same as x to the negative 3rd power. And now I can apply the power rule. Bring the power down, reduce the power by 1. So negative 3x to the negative 4th, or that's the same as negative 3 divided by x to the 4th. One thing that I've noticed here in how the book will give the answers, try to avoid negative exponents in your answers if possible. Okay, I'd want to write this in a fractional form rather than circle this result here. Okay, now here's another example. Y equal the cubed root of x. Well, the cubed root of x is the same as x to the 1/3. And that's how I'd want to think about that, because now I can use the power rule, right? The derivative of y with respect to x, or dy dx, would be 1/3 x to the negative 2/3. And rewrite this so that the exponent is a positive. 1/3 x to the negative 2/3 would be the same as 1 over 3 x to the 2/3. And then here's another thing that I've noticed in how the book will be given the answers is usually if you have a function that had a radical to begin with, you'll give the answer in radical form, usually, okay? So x to the 2/3 in radical form, that'd be the same as the cube root of x squared. And I'd circle this answer then. Here's another example. Y equal the cube root of 5. Now, what some students might do is they might want to use a power rule on that. You don't want to do that. The cube root of 5 is just a constant. And the derivative of a constant is always 0. So y prime would be 0. Okay, let's go back to the tangent line problem. And in that problem, we were wanting to find an equation of the tangent line to the graph of the square function at the point 1, 1. Okay, and the way that we were doing it previously was by limits. Okay, and we were looking at the limit of the slopes of the secant lines is the slope of the tangent line. Okay, and that's fine. You know, that's a good way to introduce the idea of limits. But I just needed to know the slope of this line, and then I could use the point slope formula. Well, the derivative of a function at a number is the same as the slope of the graph at the number. So f prime of x, well, that'd be 2x, right, using the power rule. And I would like to know the slope of the graph at 1, right, x is 1. So m would be where I'd plug 1 into the derivative. 2 times 1 is 2. Again, way easier than using the limit definition, right? So we're saving a boatload of time now by using the power rule, and we'll also be saving huge amounts of time using these other differentiation rules that you'll see in the coming sections. Knowing that the slope of the tangent line is 2 and that line is going to pass through the point 1, 1 means I can use the point slope equation now. Y minus 1 is equal to 2 times the quantity x minus 1. Rewrite that in a slope-intercept form. Okay, if you add 1, y would be 2x minus 2 plus 1 is y equal 2x minus 1 would be the answer on that one. And that's what we had before, when we were looking at this stuff back in chapter 2. Okay, here's another theorem. If f is differentiable and c is a constant, then constants can come out of derivatives. Okay, so let's take a look at a proof of that. I want to show that the derivative of a constant times a function is the same as the constant times the derivative of the function. In other words, constants can come out of derivatives. Well, let me start with the limit definition. I need the limit as h approaches 0 of the difference quotient. So here's what I'm differentiating, the constant times a function. Okay, and c times f of x plus h minus c times f of x all over h would be the difference quotient. Now, c is in common to these two terms in the numerator. I can factor that out. I know that constants can come out of limits, right? That's one of our limit laws. So I can go ahead and pull that in front of this limit here. And the limit as h approaches 0 of f of x plus h minus f of x all over h, well, that's by definition how we define f prime of x. So I've got the constant times the derivative. Well, that's what I needed to get to, right? So to me, this is a very easy proof. We can draw the conclusion right away that a constant can come out of a derivative because a constant can come out of a limit, right? A derivative is defined as a limit, and we already know constants can come out of limits. All right, so let's take a look at some more examples. Suppose that we have the function f of x equal 3x to the 4th. Well, f prime of x would be, 3 is a constant, so I just leave that constant alone and differentiate x to the 4th. Use the power rule, bring the power down, reduce the power by 1. Okay, 3 times 4 is 12. 12x cubed would be my answer. Here's another one. G of x equal 2 over x. Well, that's a quotient. Okay, I haven't talked about the quotient rule. We'll see that in the next section. 2 over x, that's the same as 2x to the negative 1, and that's how I'd want to think about this expression, because then I can use the power rule on x to the negative 1. 2 is a constant, I'll just leave that as is. Use the power rule. Okay, you're going to bring down the negative 1, reduce the power by 1, so it's negative 1x to the negative second power. And you'll rewrite that then as negative 2 divided by x squared. Again, avoid negative exponents, when giving your answers. And of course, like anything else that you do in math, simplify as far as you can go. All right. Another heads up for what's going on here in the book. Okay, we're going to be learning these differentiation rules, but one of the things that I want you guys to notice is that there's going to be lots of simplifying going on. Okay, and this is where the algebra really kicks in. Okay, you're going to be needing to simplify as far as you can go, okay, like you would anything else in math, but they want to try to make it a habit, because you see what's happening now is we're learning the differentiation rules, okay, the shortcuts, but then what's coming after is we're going to look at all the application stuff, okay, kind of towards the end of chapter 3, and then all of chapter 4 is all applications of the derivative. And in a lot of those problems, you're going to have to take a derivative and either set it equal to 0 or set it equal to a number and then solve. Okay, so you're going to be, you'll have to simplify anyway in those sort of problems. And they want to make that kind of a habit here early on. So consider that, when you're doing these homework problems, simplify as far as you can go, of course. All right, here's another one. Y equals 6 times the square root of x. The square root of x is the same as x to the 1/2. And of course, I can leave the 6 alone when I take the derivative. Bring the power down, reduce the power by 1. Half of 6 is 3. 3x to the negative 1/2. That'd be the same as 3 divided by x to the 1/2, or 3 over the square root of x, if I give my answer in radical form. Give your answer in radical form if you were originally given something in radical form. Okay, I mentioned that earlier. Here's another one. Y equals 1 divided by 2 times the cube root of x squared. So I'm going to rewrite that with an exponential notation here. So the cube root of x squared, well, that's the same as x to the 2/3. And 1 over x to the 2/3, that's the same as x to the negative 2/3. I got a 1/2 in front of that. And now I'm ready to use the power rule. Okay, I'll leave the 1/2 alone. Bring the power down, reduce the power by 1. And negative 2/3 minus 1 is negative 5/3, right? And now I'm going to simplify. Okay, the 2's will cancel there. I'm going to be left with negative 1/3 x to the negative 5/3. Or that's the same as negative 1/3 times 1 over x to the 5/3. X to the 5/3 in radical form would be the same as the cubed root of x to the 5th. And so this would be my answer in simplified form. Here's another thing that I will see students do. This is a notational mistake that I will see on occasion. Be careful about using the equal sign. Okay, some students want to get carried away with the equal sign, and they want to say equals, 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 everything is equal to everything, and that's a problem. Okay, y and y prime are not the same thing. Okay, so you wouldn't want to just write equals without writing y prime. Okay, because then you're saying y is this function and y is also this function. Like y is, both of them at the same time. No. The derivative is different from y. Okay, so it's important that we write y prime or dy dx or g prime, whatever the the derivative notation is that we're using for that problem. Make sure that that is written. Okay, and of course, definitely don't just start writing an equal sign and computing a derivative without having that there. That's it's misleading then, okay, because it looks like a function and a derivative are the same. They're not. And it also technically would be a wrong answer then, okay, because you're saying the function is the same as the derivative, which it's not, okay. We'll stop right here, and I'll get back to this in the next video.